Hello to everyone. This is another demo that uses convection diffusion in 2D. So the equations and the geometry are shown on the screen. So we are going just to set up the geometry to 10. So the length we set it to 10. So this is can change the nodes to snap it to be exactly what uh, we would like to have as dimension here. So that 9. So we have about 3 by 10. A 3 by 10 dimension. So 12 here. So we just put 12 there. This is 12, 9. This is 2, 9. This one should be 6. And by default, there is a setup of two equations inside the geometry. We remove one of them. We then update this one to a 2D one that we would like to use. This one, we remove the y variable, we remove that. So this is a 2D convection diffusion problem. So we have 4 parameters here. So those parameters could be set to be any mathematically valid equation. And then we're dealing with one element in the array. So we put it to 1, and then we can set up the value for the parameters. So for the Vx, let's set Vx equal to 1. Then we set the value for the source term. We set k multiplied by the power of w, power of p. We set that those values equal to 1. That one also equal to 1. Those values equal to 1. So we go in the domain parameters, we set the value of p equal to 1. The value of k, we set it, let's put it a negative value equal to 0.2. We would like to set k to be a negative value, so let's put k to be minus k. So this is what we have here. We have that, it's set up. The 4 parameters there have been set up. Then we set the boundary conditions, inlet, and then we set the inlet value to 1. The outlet, we set the outlet boundary conditions. This one is the adiabatic boundary conditions. We set it to opaque. So K effectiveness, we set it to 9 because it's a diffusion type from the inside to the border. So we set it to minus value. This is 1. We set this is to 0, and those are the values. And then this one is adiabatic conditions. So after we have set this way, we set the initial conditions, let it be to 0. Then we can then compile and run. We compile, okay. Then we we just run now. So the running, so the numerical result as shown in the background, yes, to show the graphical results. So these are the graphical results that we get. So it's a 1D, so the same value, it's a 2D instead, it's a 2D, so the values are changing from Y direction to X direction. So this is the value for that. So this is the way we run it. It's quite straightforward. We can show the mesh if we need, so that the mesh, and then we could show also the nodes, the mesh, and the corners of the mesh. So apart from that, we can still draw a line. Along the line, we can draw the values along a given line. So let's make it a straight line. In this case, we can make sure that if it's a horizontal line, we make sure that the y's are the same. If we want the y's to be the same, we just copy this y here. Look at that. And then we set it to be the same y. And then we take this one too, and then we set it to be the same y. So this is a horizontal line. And then we can just place more than 10 points and then plot along X direction. So by clicking there, we have our plot along the X direction or along the line. So this is the result for this convection diffusion problem that we just showed here. So we can then do another demo by then changing this equation to another one. So we remove the diffusion term in terms of X. We change the boundary conditions at the outlet. We change also this one. It's the same. It's the symmetry, which is basically the same as the adiabatic in this case. So since we don't have any derivative in the second derivative in the X direction, we use a different type of outlet boundary condition, which is a numerical boundary condition. This one is good whenever we don't know if the second derivative exists or not. So by doing that, we come here, we just change, instead of this continuity, we change to the other continuity equation. Then we shall run and see the two results. So we just have to run the problem, and that will be it. Continue. So we get the result, display them. The result look basically the same. So this is the other result by using the other boundary condition. The other one is numerical boundary condition. The other one was a continuity equation. So this is the solution for this convection diffusion problem. So the problem is solved in that case with that boundary condition. But then we can still, now we run it by changing the actual equation. So we remove the terms in X. We remove it. So this is what we have: convection in the X direction and diffusion in the Y direction, and then no diffusion in the X direction. By doing that, so we have three parameters now. So the other one has been removed. We close and we run again. Continue. We have the result. So this is this result. Let's compare the two and see how they look like. They are slightly different. They are slightly different, but not so much. Not so much because the problem is surely convection dominated, but it's slight difference in this uh, direction. So we show how to use the convection diffusion problem. So these are the results for the other case, and these are the results. So the numerical results show that there is some kind of difference when we look at the two uh, numerical results. So this is done for this demo. Thanks for your interest in using CKFLUIDSOFT.